after we found that there was clear differences in the means of the total dissolved solids of these five different recipes from the overall test, we decided to follow it up with a contrast, which was to compare, is there a difference in the average of the means total dissolved solids of those recipes that were brewed with the temperature of 5 and the average of the total dissolved solids when the coffees were brewed with a temperature of 22. To do this, we constructed a contrast, which I'll call C sub 1 here, and the contrast coefficients were 1/2, 1/2, negative 1/2, negative 1/2, and 0. Now, we might want to do more than just one contrast here. So we could also consider a second contrast, which I'll call C2. This contrast is going to have these contrast coefficients: 1/2, negative 1/2, 1/2, negative 1/2, and 0. Stop and think for a second. What hypothesis is this second contrast correspond to? We have positive 1/2 coefficients for the recipes where the method is drip, and we have negative 1/2 coefficients for the recipes where the method is immersion, except for the case here, recipe 5, where the temperature is 98. So remember, this is that case where we have the sort of standard French press brew where the hot. So it's sort of an odd man out kind of a recipe. So what does this C2 correspond to? Well, it corresponds to testing, is there a difference in the average of the total dissolved solids comparing recipes with different methods. So methods with drip, take their average mean total dissolved solids and compare that to the average of the total dissolved solids for the coffees brewed with immersion methods. So we can write some notation for these contrast coefficients. For here, we might write that this contrast coefficient here might be C11 is 1/2. The second contrast coefficient here we might say is C12. That also is 1/2. C13 was negative 1/2. C14 is negative 1/2. And then C15 is 0. So it's not C15 or C14, it's 1, 4. So the first number corresponds to which contrast we're interested in, and then the second number corresponds to which level of the factor. So in this case, which recipe. So for our second contrast, C2, we have C21, that's 1/2. We have C22, that's negative 1/2. We have C23, that's 1/2. C24, negative 1/2. And then C25 is 0, just as in the other contrast. So here is where we start talking about what we mean by orthogonal. So a set of contrasts, so we'll call it C sub j, are said to be orthogonal. So call each contrast C sub j. We have C1 and C2. If the dot product of the contrasts are equal to 0. So what do we mean by the dot product? Basically, if you take the sum of Cp sub I and you multiply it by Cq sub I, and you add all those up from I equals 1 to A, this should equal 0 for P not equal to Q. So P and Q are just indices for our contrasts. So in this case here, P might be 1 and Q might be 2 here. Then, if this is the case, we say that C sub P and C sub Q are orthogonal. Why does it matter if our contrasts are orthogonal? Hang on. So why do we care if our contrasts are orthogonal? Is because if we have a set of A minus 1 orthogonal contrasts, those will completely partition the sum of squares treatment. And their primary benefit is that all of the tests that we do, these contrasts, these different comparisons of means, will be independent of one another, so that the result of one test won't affect the result of another test if they're orthogonal. So we'll see more examples of using orthogonal contrasts in the examples to follow and throughout the course as we go.